Hello everyone, welcome to today's session on dependency management for C++ applications using CMake and Conan. My name is Kunal Sharma, as very well introduced by Shilpa already. I work at Infineon Technologies, and let's just quickly look at what can you expect from this session. I believe that after this session, at least you would get a very good idea on writing a CMake file. Similarly, also creating and installing CMake packages, writing a basic Conan file in order to basically interact with the artifactory. Similarly, also getting the packages from the Conan artifactory. And the last key point is that utilize open source more efficiently. Utilize the things that are already there in the open source directly from there instead of doing the things repetitively at our end. So this is basically a very good picture which shows the everyday struggle of a C++ developer, where we always get this excuse for slacking off that my code is compiling. Yeah, and there's not much that we can do here, at least from the performance point of view. But what we can actually do is reduce the redundant builds. So do we have a possibility? We'll see that. So what is actually the need for a dependency management system? Why should one put a bit of an effort in doing this kind of a setup is, let's say you have two developers. Let's call the developer on the left side a bit senior, and on the right side someone like me who has freshly joined a new organization. Now if I get introduced to a new project, I should also be made aware of the dependencies that the project is using. And now if there is no possibility of sharing those dependencies, then I myself have to go again through the iteration of basically building the dependencies at my local machine, which would take some really good amount of time and effort. So there is no possibility for binary package collaboration. Yeah, at least not a really good mechanism out there. You might be using some kind of a network drive in order to store those dependencies, or maybe you might be using gateway, which is not the ideal way since it's better uses for the source code. But there's not really an ideal way of sharing those binary packages. Similarly, within the organization, there are various teams, and all of these teams would be using some kind of similar dependencies. Let's say you might be using Boost, you might be using GTest, you might be using Qt, and people from this different teams would be maintaining and managing these dependencies on their own in a very different way. So there is no uniformity within the organization or within the team, as we can see. Yeah, can there be a unified mechanism here that we can basically take at the team level or maybe at the organization level, and everyone basically uses that for getting their project dependencies? We need to look here. Then let's say in the presence you have a library A built up. Let's call it a very it was a difficult task to get this build, maybe due to some compiler flags and everything that you needed to get the context of. And in the present you're really happy that you were able to get it. But what if in the future you again require that dependency at you do not have that binary package in your machine, or maybe in the place where you get it from? So you'll have to go through that same build process again. Yeah, which would basically keep on adding on whenever you had this need in the future. Yeah, then also there are a lot of many things which are already there in the open source community. A lot of things have come out, mainly like binary packages, sources and everything which are there. But we do not really have a direct way, at least I don't see a very good way of going and getting those dependencies. Maybe you might go and clone some sources from the GitHub or something like that, but then you also go and build it, and then there's a lot of man effort, or let's say manpower involved, right? So instead, how better it would be if we basically get some mechanism, or let's say some setup where we can directly look out for some dependencies which might be there already in the open source. And of course the common things which are being used like Boost, Gtest, Qt, as I mentioned, System C as well. So these things are readily available within the open source community for your use. You just need to have a setup called dependency management, which checks out all of these issues in a very seamless manner. So let's just answer some of the few very quick questions that might come out in your mind initially. So what is the dependency management? It is basically a technique for handling your project dependencies in a very automated fashion. Dependency management system, or the technique or the system that we'll be focusing today, would be a combination of a build system and a package manager. So what is a package manager? It is basically, it helps you in configuring, upgrading, installing, removing packages in a very consistent manner. So there is very minimal human intervention involved, and everything is basically done in a very clean way. A very good example of a package manager, we can take it as pip, which does a very good job in the Python world. But unfortunately, we do not have such conventional package managers in the C++ world. At least they do not come directly. You need to have some setup done, and we'll see about these in the later slides. Then also the build system. If you have some assets of your project that need to be basically transformed into a usable product, and if you have let's say a huge project, or maybe at a medium level, you certainly should make use of the build system instead of doing the things manually. Of course, that is a very let's say lame idea, because we already know that how important or how crucial build systems are when it comes to the C++ projects. So yeah, these were very basic definitions that I just wanted to cover. And now, what are the various common build systems available within the C++ world? So the first idea that I guess would everyone come to everyone's mind is Make, which comes from the GNU community. Similarly, but writing these scripts in complex projects is not really that easy. GNU also provided another improvement over the Make with the help of auto tools, but it turned out to be way more complex as a build system. Then we also have SCONs, which is a very easy to use build system, I would say, which is Python based. You need to, so you get all the flexibility from the Python world, but it is really considered to be very slow when it comes to performance and efficiency. We also have another build system which is commonly used, called as Premake, which is something similar to the next one that we'll see. But Premake basically uses Lua for its scripting. And if you basically go and check out the scripting mechanism used by CMake, you wouldn't get an idea of what it is doing by directly looking at it. So it's basically a complex to understand, and hence a bit complex to write as well. The one choice that actually I had, and actually the one that I extensively got time to work on, was CMake. And this has been a build system which has got a wider acceptance within the community day to day, and also has basically shown a lot of contributions from the developer side with respect to standardizing this tool. So what is CMake and why should one use it? CMake is a platform independent build system generator. So if you are confusing that CMake is a build system, it does come in that family, but it's actually a build system generator. Platform independent here simply specifies that you can work it out with Linux, with Windows. CMake doesn't really have any issues in that. But what is actually a build system generator? It basically generates your build intent. So if you run your CMake script, you would get a solution file created out of it, maybe a make file as per the generator you specify. And since the native build intent is being created, they tend to be much more efficient when it comes to performance. Also, you do not need to worry about the amount of generators that are available within the CMake. It's really a wide pool, and I am sure that you wouldn't be left with out of choices. Now, how to generate this build intent? So firstly, I would like to show one thing. So let's just say I just run the CMake help command. I hope you guys are able to see my command prompt that I've opened. And
Kunal,
yeah,
can you increase the font size?
all right. How can I do that with the CMD?
Uh,
Right click on the top bar.
Mhm.
edit.
property.
Sorry, properties.
Hmm.
Then font, not
Okay,
cursor,
sorry. Okay, okay.
font. Then you can just make it 24.
24.
All right. All right. Is this better?
Yeah, it's
Yeah.
Okay. Okay, great. So as we were discussing about the various generators in CMake, so generators by default it automatically selects Visual Studio 16 2019 that is already installed in my machine. And similarly, you also have here, if you can see, Unix make files, Ninja, code blocks, then Sublime Text, Eclipse. So various, the common build systems or the build intent that you would use in your project, you already get those options within the CMake. And this generators that you're seeing, the list goes on much more, but basically these are available for the platform that I have at the moment. Yeah. So now, how do you generate these build intent? You need to write one CMake list file, the basic script for a build system, which we always have to, and then you specify CMake path to your CMake list file with the generator argument as you should have specified. Here, the generator specified would create a 32-bit project file. If you want it to be 64-bit, then you have the option of specifying one more argument with hyphen A, with a capital A that basically represents architecture, and then you can specify x64. So a 64-bit project file would be generated. So this is basically the idea. Mainly, the compilers that we might use when it comes to C++ is GCC, Clang, and Microsoft Visual Studio Code. And CMake is a very good option when you can consider these for the build system. Now, how can one write a CMake list? So it's not that really direct, but I'm really sure here that once you get the idea of writing a basic CMake list or txt file, you can just modify it in all of your projects and at various places, and it takes no time. So you just need to get the initial setup done. That is where some effort might be required, and after that it's all a very minimal effort and few minutes of changes. So this is a very important statement that I would like to highlight. So CMake earlier wasn't really recognized as a very good way of the way in which CMake scripts were written, but after CMake, I believe 2.8, or let's say just say CMake version 3, CMake transformed itself into the modern CMake aspect with some standardizations being done at their end. And now, how do you what is the modern CMake approach? It basically suggests that you must write your CMake list.txt files, which should be target specific. Now, okay, I get the idea that I should write my CMake files which should be target specific. But what exactly target means in respect to CMake? So targets, if I have to put up in a very simple way, I would say that they are the high level logical placeholders useful in generating the various useful products from the build process. This is a very minimal example or a skeleton of a CMake list or txt file. And here, if you see, I have just specified what you need to specify at the very top is CMake minimum version that is required, and I've specified 3.15. So if CMake is basically saying that if you want to run this script, you need CMake 3.15 at least installed. Yeah, if you have something below 3.15, it wouldn't run. Similarly, we have another command called project demo. Then demo is basically the name of my project, and if I just run the CMake script, so a demo.solution file. So the project file that would be generated would be with this name. Then add executable demo. So the name basically directly suggests that I am trying to create an executable here. But what is this demo? This demo is basically a binary target. Then I just say that I want to create an executable which would be represented by this target, and I provide the sources of this target with the help of one variable called CMake current source dir, what does this represent? This represents the path to my current running CMake list.txt file. And then I say that, yeah, my source file is in the same directory, and I specify something called private, which is the scopes in CMake. There are three types of scope. You can relate it with the inheritance concept, but we'll also see how these scopes are different and everything. So we have three major scopes in CMake, or let's say three scopes: public, private, and interface. So now let's also try to basically see and get an idea of how would something running in the CMake file would look like. Is this text visible, or should I just increase its size as well? And
Please increase. Please,
sorry.
please do it.
Okay.
Increase, Kunal. So
Okay. I really forgot that how we used to do it. Can somebody help here?
just press the control and scroll your mouse pad or the mouse trackball. It should increase.
Okay, yeah. Let's just see. Okay, sorry. But the size hasn't increased. Okay, yeah, no. Okay, I might have to do it for all the folders. No problem. So, if I go inside this build directory, what I really have is one demo.cpp file, one CMake list, and this demo.cpp is nothing but just a hello world file. What my CMake list stores is nothing but the CMake list that we just saw. And now I have another folder called the build folder, where I would like to generate the build, the products from the build process. So if let me just give me just 2 minutes. Okay, sorry.
So just go back and go in the project explorer.
Mm-hmm.
Just hit back button.
Oh, okay. It is taking that CMD only. Okay, sorry. Yeah, so now, as we had already seen, I would simply run a very simple command which would configure my CMake script and basically generate some things out of my CMake list. As we had already seen, the one command where we specify our CMake, then path to our CMake list, since it's a level up, so I've specified it, then the generator that I want, and the architecture. And if I simply run this command, what CMake does is, firstly, it tries to identify my C++ compiler, what it is. And then what I would like you to see now is that if I go in my build folder, a lot of files have been generated, but the one that I would really like to focus on is the demo.solution file, which you can now directly use for in your Microsoft Visual Studio Code for your project development. And another file that I would like you to notice is the CMake cache.txt. What does it store? It stores all the information that is provided from CMake to the build system, the various flags, optimizations, and everything. And this file is basically used by CMake in the next subsequent runs of the CMake list file. If you run this CMake command again, then CMake would try to fetch most of the properties from this file, and if some of the properties overridden, then the overridden properties would be updated in this file. Now I just want to build my this solution file. I'm not going to build it from the Microsoft Visual Studio Code, because even though you have the option of it, but I would like to go by the CMake command, because just to be here be platform independent, meaning how do you run the same command in all the generators. So this is the command for building, uh, where I would specify cmake hyphen build, and then since my project is of type release, or I would like to build it as release, then I would just say release configure, and then basically I get my exe. and it says hello world. So now what exactly happens is that in the case of Microsoft Visual Studio, you have this option of specifying the configuration during the build time. But if in case you are using something, let's say like a make file or something, then CMake has this another variable called CMake underscore build underscore type, where you specify the build type like release or debug while configuring, or let's say while generating your build intent. So it should basically come out at the very top. Now we just saw that how a basic CMake command and everything can be run. So let's just skip right into the libraries portion. So CMake says that it has easy integration of libraries. A lot of libraries, if you would have been using like GTest, System C, or Qt, recently also got itself CMake compatible. So they are basically adopting CMake as their build system. Why? That is the question that we would see. So add library, just similar to the add executable that we just saw command, where I just want to create a target called calculator. This is basically my library target, and I'm specifying something called static. What is static? Static basically means that I want to generate a static library. Similarly, you also have the option of specifying shared or interface. Interface represents the header only libraries, whereas shared would get you a dynamic library created from this target. Now target sources, I just specify the sources as we had already seen. And then another commands come which is very important, that target include directories. So I'm just specifying an include directory where my header files are present. This is basically the -i flag that you basically specify while running the code manually. So just this basically represents the directory to my header file, and I've specified the access specifier or the scope here as public. We'll exactly see why. Now I'm also creating one main which is using this calculator library, which basically has some dependency on the calculator library, and then I specify where my main file is, and in the end I just link this main target to the calculator one, because in order to get the linking and everything working fine. Now here you see what we actually did is we specified everything with respect to a target. What we another thing that we did is we reused that same target, and we didn't have to do anything. So we just said that main link this target to the another target, and that's it. The public properties of this target would be provided, or let's say would scale up to this main target. So this directory path that I was specifying as public, this -i flag, would actually scale up to this main. Let's also try to see this example in this case. So let me just go back to where my calculator demo is. And if I run the same command again, I just want to show you guys one thing. So, yeah. Now, if I go back to my calculator, and if I go inside build, my solution file is already generated. All right. Yeah, so now if you can see, basically two targets here CMake has provided, calculator and main. Usually you do not basically write the targets of library and binary, I mean the executable in the same file, but here we have, and that is the reason that the CMake list for both of them is actually the same. So here you can also see that Visual Studio was aware of the CMake list file, and it basically gels up with the CMake list.txt in a very good way. You can modify your files here, and then basically run your build, and CMake would take care of everything. Another thing to highlight here is that within my CMake list, if you can see, I'm also specifying the header file for the library. It isn't really necessary, I would say, because a library is what a bunch of compiled object files, an archive of those. And the header files that we need to specify is mainly because we also want these header files to be shown here in the Visual Studio project. So that is the only requirement. And just to make you guys show, then my main.cpp is basically including this calculator and doing something, doing some basic addition. Now, if just let's just confirm the things. So yeah, it did the calculation. So I guess this is mathematically correct, and we were able to run our program. Another thing is that if I go inside my release directory, I can see my main.exe created as well as the calculator library created. So this is how simple it is to create, or let's say generate targets, usable products from CMake. And one highlight we should focus on is that following target specific approach allows you to bind properties to a target, just as we were doing in case of calculator, and avoid conflicts at the global level. So earlier, in the earlier versions of CMake, before the 2.8 version, I believe, everything within CMake used to be specified at the global level, which basically meant that even if you do not want to use that build flag in a certain scenario, you still have it present in your project. So it wasn't really a good way. Then also another important aspect that so here we just bind those things to a target, and using that and then reusing this target at some place means reusing all its properties here specifically mean that public and interface properties. So here if you see line number 16, I just reuse that calculator target, and all of its properties like the header file path would come out, and my main is basically able to compile everything and run fine. So now coming to the main question, what are the scopes and CMakes that we just discussed? But let's also see them a bit more. So let's say I have a target B, which requires target A, and now my target C requires target B. This is basically some sort of a transitive dependency that we are seeing. And let's say my target B linked to target A as public as its scope, and now target C, when it links to target B, no matter be it public private interface, it would also get the properties of target A transitively from target B, since target B is linked to target A as public. If we come look at the same case where target B links to target A as private, then when target C links to target B, it would only get the properties of target B, not the properties of target A. In the case of interface, the things turn out to be a bit interesting, as we already also mentioned that it's also quite relatable to the header only libraries. So what does it really mean is that target B is linking to target A with interface as its scope, and target C links to target B. Now target B, why does it specify interface as its scope is that it is saying that I may not use you, I might not consume you, target A, but anyone who consumes me would also get you. So once target C links to target B, it would get target A as well. Yeah, so this is basically a way of also specifying transitive dependency, but with the exclusion of using it in the midway path. Then we come.
Kunal, I
Yeah.
want to interrupt you. Can you go back to the previous slide? Okay. So this only stands for the using the APIs, or these also affect the debugging?
Yes. So certainly it. I didn't get your actual context with respect to debugging.
Okay. So when I compile, let's say target A and B is linked private, right?
Mm-hmm, mm-hmm,
And it is already generated. And when I
mm-hmm,
compile target C with the
mm-hmm.
dependency of target B,
Yeah.
right?
Uh-huh.
With the debug option, then
Mm-hmm.
is I mean the functions or methods of the target A will be available for us or not? I mean.
No, no. If you use private, so that is the point that if you use private here, then
Mhm.
next you have to basically yourself specify that you also need to get the target A.
Okay.
Yeah, since target B isn't providing you that, so you need to here basically the same way you're linking to target B, you need to also link yourself with target A, else you will get
Okay.
errors. Yeah, linker errors.
Okay.
Yeah.
Okay. Got it.
Now, mhm,
I have one query. Can I ask?
yeah, sure.
So can I like, is this something like there is in classes public-private thing? So like, is it similar to that scopes
Uh,
in C?
these are the scopes in CMake only, right? Oh, you're mentioning those the add library. Oh, sorry, this. Where was it? The libraries that we were creating, there was also interface. Were you mentioning about this?
No, I mean on a theoretical level, is it similar to how there is scope at C++ class level?
Yes, yes, it is similar to that only. The only difference is that another aspects comes out, which is the interface instead of the protected one. And as we already said, that target B links to target A as interface, saying that I do not need it, but I will provide you to someone who links with me. The only difference is that mainly you can also, just as I earlier mentioned, is that you can relate these scopes with the inheritance properties that we have when it comes to OOPS. The only difference is with respect to interface.
Okay, it's clear. Thank you.
Yeah. Okay. Okay, then create now coming to basically not first creating CMake packages but consuming CMake packages. So we have a lot of open source libraries which are CMake compatible, like GTest and Qt, as I was saying, and we build them at in our machine with by using CMake. But how do we actually use them in our projects is the way we need to look at. So CMake has a call called find package, which would basically find an external package and loads its setting. By saying external package, it is basically a CMake package. Find package works only for with respect to CMake packages, of course. And then there are two ways of using find package, which is module and config. The only way that I've at least seen till now, and most of the cases, config way is the way to go. Of course, module way is also the one. By default, if you do not specify anything here, then CMake would go first about the module way and then the config way. So you need to specify the things that the config. You need to specify this config keyword. We'll see exactly how the things are being working and everything, but just that I wanted to specify, and we would be concentrating on the config mechanism. Now find, I'm just saying in somewhere in my source code that find me this package which is called GTest. I'm saying that my configuration is this. Sorry, my config, I want to use the config mode, and I'm also specifying this keyword called required. Now this may not look important, but actually it is, because if you do not specify this, then CMake would continue its execution even though it wouldn't be able to find this package. That is not what we want. If we should specify required, so that if CMake is unable to find the GTest package, which is this external package name, then CMake should stop right there. Then also for linking the libraries, we use the same way. Here we just specify the external target with its namespace. So this is similar to what we generally use in C++ world, where if we are basically trying to consume something from the external thing, then we specify the namespace and then use it. Yeah, so GTest also, while creating its package somewhere, would have mentioned a namespace, and in order to consume its target, which is now, at least in this case, external, so that is why you need to use it with the namespace. Then also we have seen that how we can basically write these things out in the find package, but we need to specify, we need to tell CMake where exactly this GTest package is present. So for that, find package would basically look for the external package with the help of a variable called CMake prefix path, where you which would basically represent the path to this directory where the GTest package is present. So let's just also quickly see one quick example of consuming a CMake package. So I already have the GTest package installed in my machine. What I really need to specify here is let me just go there. No. All right. So yeah. Oh, maybe use the same CMD. Another thing that I wanted you to show you is that here my CMake list, as we saw, that would be calling out the find package of GTest, meaning that it would be used in the case of some testing requirements. So that is why I'm also creating an executable called calculator unit test, and out of that executable I'm creating a test. Now creating a test in CMake is also very simple. Once you have your executable created, you just say that add test, this is the command, then the name of your test, and command which is the keyword that you need to specify, and after that you can specify your executable. CMake would put this executable in the command line and run this executable while running your test cases. Now we see the rest of the code is something that we had already seen, and now let's just run the CMake config command. Here I need to specify one more thing. So if I go back to my CMake list.txt, we do not need to look the entire CMake list.txt, but what I want to also show you guys is basically the option. Here I'm specifying that build test should be off. So meaning if I run this CMake normally with the same command, then it wouldn't build my test. How is this option being used? It's being used in the very end. If you are able to see, then basically it just goes in this. I am just putting an if condition where if build test is set to on, then enable testing. Enable testing would create one file called ctest test file, which stores the information about your testing, which you have specified with respect to your add test. And then I'm adding this subdirectory test. So CMake would go in this directory test, and then the CMake file that is there in this directory would be executed, which is nothing but my CMake file, which implements the testing logic with respect to the find package and everything. So now since I had specified my build test as off, I don't want to change it in the CMake file. What I would actually, where I would change it is while running the CMake config command. So here only I'm overriding that thing. And also, as we had already discussed, I need to specify another variable where my gtest file is, and where is it? I already have its path. So then basically I have specified the gtest path here with the prefix path. So I'm just saying that my gtest package that I've created is here. And all right, maybe I didn't clean up this build test folder. Let me just do that. Yeah, now we should be good to go. So here, since we were using the add test mechanism, which basically relates to some extensive functionality provided by CMake, which is called ctest. So we would see that some file called ctest.test_file.cmake has been created, and what it basically contains is it's saying that go inside the test directory. Now, if I go inside the test directory, there's another ctest file. If I look here, then it says that basically run this executable. Yeah, it provides the path to this executable saying with the add test command. Now I have to build my test case as well. So let me just run the CMake build command. Yeah, exactly. So now I see that the test binary that I wanted to create has been created. I just need to run one ctest with the configuration option. So since my test has been built as a release type, so I would specify the configuration as a release, and then I basically run it. Also, this doesn't really look well, so let's just increase the verbosity. So here now we can see that we didn't specify anything other than the GTest target with respect to the find package and target link libraries, and CMake was able to find my GTest library, put out the GTest flag here, and run the test cases, and also show out what exactly happened, which is coming out from GTest only. So this is basically the way by which you can consume a CMake package. And in the consuming CMake packages, there's also one exception with respect to Boost. So Boost doesn't really use CMake as its own build system. It has its different build system. So that is why CMake provides a mechanism of using Boost library with the option called find boost.cmake. You can go around and search about it. There are various things that CMake has implemented in order to basically make Boost compatible with CMake. But if we simply look at it, it says that find package Boost. Here we do not specify config because it basically generally uses the module way, and as the name suggests, find Boost, and then we say out required. Then also Boost, as we know, that is a bunch of multiple libraries. It's not just one library or one it contains of various libraries. So let's say you require the file system component from Boost, then you say that I just require this thing, and CMake would just go and look for this file system file library and nothing else. Then you just link your target. How you link it is with the Boost namespace. You provide the component name like file system. Now we come to a very interesting aspect in CMake. Now we have seen that how we can use CMake file, I mean CMake package, but we should also be able to create a CMake package. So we need to see that how we do it and what are the things required. So install export in CMake. So install export feature of CMake allows you to distribute and consume packages. To the export command lets you export your target, as the name suggests, from outside your build tree to external projects. Similarly, install command lets you install some necessary files and everything inside your CMake package that would be created. And then to create or consume a package with CMake, you need three important things, at least with the config mode I'm talking about. So you need a config file, which would be the very first file that CMake looks for when you specify find package, package name, config mode. So CMake would just go directly and look for this config file. Also, you have a mechanism of specifying version in the find package, but I wouldn't really recommend that. Only reason is that we should leave out the versioning things to the package managers, since they're way better at handling these things. But if you need to specify, then and if you specify some version, then CMake would go from the prefix path, CMake prefix path variable, go to that location and look for this version file. There's also a way in which CMake iteratively uses, or let's say looks for these files. You can search that out on the CMake documentation. And then also we need one targets file, which would show the information related to our targets. So in order to CMake wouldn't search for this targets file, so what we need to do is link this config file with the target file while creating our package. Thankfully, you do not need to write these files. These files are basically generated, and the main ingredients behind generation of these files is that CMake package config helpers. This is basically one macro which you can include, and what it does is it provides you two helper functions which are important for generating the config file and the version file. And now let's look at how exactly the script looks like. It is just like a very few lines of code, and it will generate an enormous amount of files for you. What we are doing as an initial step is we are specifying include the CMake config package config helpers, so that we are able to now use these functions. If you do not specify this include, then these things wouldn't run, even if you basically specify them in the right way. So firstly, you need to specify this macro, then you specify two helper functions which are important. You specify something as an input to generating the config file. So here I'm saying that my config file has one input. You can also avoid this, but we should definitely make use of this. We'll see exactly why. And then I'm just specifying my path where the config file would be in the build tree. So I'm saying that my config file is here in the current binary directory. Basically in my build directory, it is the config file is generated. Then I'm just saying that do not generate some unnecessary macros in my config file, make it look simple and easy to understand. Next, I'm specifying that where should you install my config file in the package. I'm saying that in the package, wherever you install the package, the one CMake folder should be created, and inside there, the config file should come out. And the last thing that we are specifying is path variables, which is target export name. Let's just look at this when we actually see the final CMake script. And then we come to the very simple helper function, which is necessary for generating the version file. We specify the path to the version file, the version. I already have the version specified somewhere in the top of this file, which is like something, and I'm just making use of that variable. So here is how you dereference that variable. And then I'm just stating out that compatibility of my project, any new version, meaning that it handles backward compatibility. So now if you specify anything newer, when it comes to find package, let's say you call out find package 1.2, and my current package is basically version 1.0 that is available, then you can use this package. In the end, my CMake file is generated. I specified the path. I mean, the config file is generated. I've also generated the version file. Now I need to install it somewhere in the package, right? So that is where I make use of the install command. I just say out that I have some files to install. I specify their paths, and then where should they be installed. Of course, we have specified the config file destination already in its helper function, but with respect to the version file, we haven't specified. So we need to specify this as well, and then both of these files would be basically installed in this directory, which is called CMake. Now let's also exactly look at this step, because digesting this information might be a bit too difficult from just the slides. So I'll just go back again to this folder. I just need to do back and then cd and cd build, and now I'll again run the same command, the same config command. Apart from it is, I need to specify one more thing. What I need to specify is where should CMake install my package, because I've already instructed CMake that how should you install and everything, but where I need to specify, and I can specify it with the help of this variable called CMake install prefix. This sounds very similar to the prefix path. So with the prefix path, we say that my package is there, go use it, and here I'm just saying that install my package here, and then basically use the relative path for the CMake directories and everything, and set up my package there. So I'll just call it out as it is again the calculator example. So I'll just say calculator package, and I hope the things would work out now. All right. So now what do? I need to build these things. So I'll just say build, but with build, I also want to state out one more important thing to CMake. That is that I'll also say that yeah, just go ahead and build my this calculator library, but also I'm specifying that now install this as well. How do you specify it? With the help of this argument saying hyphen target and then install. So I'm just saying that you'll be generating something. You have some install commands in your CMake list.txt, and with this you and telling this argument, only then the things would be installed. If you do not specify this argument, then the things wouldn't be installed. Everything would stay in your build directory. So here, if you can see, my library was created, but that is something we already know. What it actually did is it went in some directory and installed the things. Let's just see that. So if I go inside there, there should be a calculator package folder, and this is the general structure that you should follow while creating your CMake package, because CMake, of course, cannot be aware of where the CMake package related files would be present, which are always in the CMake directory. So you need to specify CMake directory for storing these information packages. What you also need to do is that, let's just go back, and if I just look at the CMake list.txt, then step by step, let's also try to analyze some more things. So I'm just specifying my package name as calculator, package version as this thing, and the next thing that I'm doing is basically I'm telling it to install my header files in some directory, because of course you can export your library, but also the header files that it requires should also be exported out. So how you can do it? You can do it with the help of install command, and you specify the destination that within the install prefix. So every path that you specify as destination would be relative to the install prefix path, install prefix argument that you specify. So it would go inside the calculator package, and then inside include, it would create an include directory, and then basically create this, copy this calculator.h file. Then also I'm just setting out one target export name. This will basically help me in exporting my target and also in the generation of my targets file. As we had seen that our package basically requires three types of files, and one of them was the target file, which stores all the information about your target. So I'm specifying that create a calculator targets. Yeah, this, the variable should represent this, and then I'm saying that install this target. Also here you need to specify that I also want to export my target. Yeah, and then I'm saying archive is basically for the static library, and then destination lib. So the lib should be the folder where my calculator library should be installed. And another thing that we need to do is, since we are exporting this thing, so we need to firstly also make use of export. Here we have just called out a name, but here we are actually doing the export of our target, where we say that this is the target that I want to export. This should be the namespace when it should be exported, and if an external let's say package wants to use it, then it should basically link it to it with the this namespace. And then I say that what should be the file that that it should have. It should be the targets file, so calculator targets.cmake file. Now I basically provide the command. I now the target file has been generated, but I also need to install it. So I need to say that install export target export name. Then the file, what is the file name? Its file name is calculator targets.cmake. Destination, it should be in the CMake directory. Namespace of the package, this is basically namespace of the target. This is what. Then now we come to the last stages that we need to I was mentioning that we need to provide one input file to the CMake package in order to generate it. So the input file name would be calculator config.cmake.in. So as you can see, it is an input file. What does it really store is basically, if I go inside my CMake directory, here it is present. And what does it really store is something we do not need to actually look at from here, or maybe we can see that as well. But what I am actually saying is that that initialize my package. So when this helper function is actually called, okay, just a second. Okay, so when this helper function is called, it firstly goes the right direct to my this CMake config input file. I'm saying that initialize the creation of my package, and then I'm saying that include CMake find dependency macro. We'll come to this last in some more time, but what in the end I want you to see is something on the line number 6, This is not the necessary part in order to make the things running. What I want you to see is the line number 6, which is very, very crucial. I am saying that include target export name dot cmake. So I'm trying to basically include some file here. So when my config file would be generated, it should have this include where some target export name is being called out. What does this target export name specify? It specifies the target file, right? It basically represents calculator targets, this variable dot cmake. So I'm just including, this is the way that you can link your config and targets file. Also, if you go here, how is my, so this target export name is being used in a very different way with the @@. So how is it able to access this variable is with the help of this pathwares, where I said that create a helper variable called target export name, which is this, and here it is aware that what it represents. So I just provide this as a helper variable, and as a helper variable I can consume it here inside my input file while basically calling out my input file. So this is how you link it, and the rest of the things we are clear. Now also let's just have one very quick look at how our calculator package looks like. So here, if you go inside the CMake config file, then what I want you to see is CMake is firstly checking out some get file name component, where it is saying that all the components that I wanted should be there. So every time the someone tries to consume this package, this thing should be run at first, where CMake tells that yeah, this package has everything that it requires. If something is missing, then this would straight out give an error. Also here you can see the include of my targets file, which has been generated. How does my target file look like? It looks like something like this. And in the end, what we actually want from our targets file is this add library command created. This add library is creating now an imported target. Imported means that it can be only read, it cannot be modified. It is a static target. It is the same target that we are creating, but with a namespace. So here, if someone now tries to basically use this package, they can directly use this target as the external target and do a find package call to this calculator package directly, and they'll be able to use it. I also installed the header file in the include directory, and lib contains my final library. So this is how generally CMake package would look like. Now let's go back. So also, just one last important aspect of how CMake handles transitive dependencies. So, which is very, very nice, at least from the perspective of a build system, which is not really good with these things. CMake is really good here. So let's say I have a library C, and library C requires library B, and library B requires library A to be built. Yeah, so if I directly call out this library C and link this library C with library B, things wouldn't work, because this library B also has some requirements from library A, yeah, in its build, I mean. So now this is basically leading us to a transitive dependency nature. How do we resolve it? In CMake, there is one mechanism called CMake find dependency macro, which helps in handling these transitive dependency issues. You have a find dependency helper function, which wraps a find package call for a package dependency. So while you are trying to create a package, your package would also be having some dependencies. So you might be in the CMake list file of your package. You would right at the source level, you would be making some find package call. But how do you make sure that the user who would be using your package also is aware of those find package calls while they try to consume your packages? So what you can do is you can just go inside your um, this config input file, and then what you can do is you can include this CMake find dependency macro and do a similar find package call here. As I said that it is a wrapper. but it is basically handling the transitive dependency. So next time someone wants to basically include or let's say use your package, use your package that has been created by you as a vendor, then they would also get some hint that this package is dependent upon GTest. Yeah, if you do not do that, then they would straight away get some linker and compilers and everything. So that is not the trouble that you as a vendor would like to provide. So your users should get an idea that what exactly is missing, if that is so. What in the end find dependency macro would do is whatever you have specified in the find dependency, it would say that our package requires this package as well, and you're missing this, so please get me the path of this package, the GTest package. So this is how CMake basically hints out about the transitive dependency. This is the final statement about CMake, where it easily gels with IDs. And some important highlights: it has extensive and extension in the form of C test for the test cases. It has extensive community support. A lot of things around CMake are coming up. It is being widely accepted within the community. These are some of the libraries that have accepted CMake as its default, or let's say the conventional build system. Also, a lot of being development is being done in the CMake world with respect to modernizing the stuff and standardizing it. Earlier, as I said, that it wasn't really good, but now you specify everything at the target level: the properties, compiler flags, build flags, and they are easily scalable, since once you link that target to some other target, those flags would also scale up if specified, of course, public or interface. Yeah, so I would say that this session we can bring it
Yeah,
down to this point.